All right, so let's go ahead and kick this off because I've actually got an awful lot of content today. Thank you all for joining us in the first of what will likely be a much larger and longer webinar series where we here at Aerotos will be presenting to anyone who wants to join and listen a lot of information about drone surveying in general. And today we are going to be talking about, as the subject of the email may have suggested, we are going to be talking about flight operations and mission planning. So what we're going to cover today, what this means is that we are going to cover specifically flight operations and mission planning for surveying, or specifically surveying and mapping in general. Now, obviously, there are a huge number of potential use cases for drones. You can use drones for wedding photography or bridge inspections or all kinds of other stuff. But today we're going to be focusing on flight ops and mission planning for surveying specifically. That's definitely where we have all of our expertise. You don't want me as your wedding videographer or anything like that. But that's where that's what we're actually going to be talking about. And within that, there are a handful of other subcategories, the real core things that we're going to be getting into the nitty-gritty over the next hour, of everything from airspace regulations, where you can fly, what are good procedures to getting the right authorization, making sure that you keep everything legal. We're going to go over your RTK system setup. What options are there out there? What are some of the pros and cons with each of those things? We're going to go over ground control point and checkpoint planning, things like that, as well as flight planning, and then, of course, flight execution. So the actual planning, the different software settings, and what are some of the good field procedures in that. And all of that put together, that is what we refer to as flight operations and mission planning, that whole stage of things that are necessary to get working so that you can actually go out and fly. And as I get started to jump into all of this, I will point out I do love questions. And doing our first webinar like this, there is an awesome Q&A tool that you have. If you hit there, 3 little shapes in the bottom right corner of your screen that might say activities, then there will be a Q&A section there. So go ahead, if anytime I'm saying anything, if you have a question, go ahead and drop a question in there. I'll see it, Mike will see it, and we'll be able to answer it. So with that, let's actually keep going. So like I said, today we are covering mission planning, everything that is required to responsibly, safely, quickly, efficiently collect good data in the field for mission planning. Now, why do we know about this? Why am I talking about this at all? We're a data processing company. That is true. That what we do is drone data processing for land surveyors and civil engineers. We've been doing it for about 10 years. And I always like to be upfront about, conflicts of interest. Why are we doing what we're doing? This isn't a sales pitch. This is meant to be as informative of a webinar as it possibly can be, truly about mission planning, because selfishly, we want to inform either our clients or prospective clients or anyone in the industry how to collect good data to make it easier and better to process. And the flip side of that is we get to, as a data processing company, we get to see the data from hundreds or thousands of surveyors all across the country, and all of the things they do right, and for other reasons, all of the things that they do wrong. So we've actually learned an awful lot more about flight operations and mission planning, and it's part of the service that we offer to our clients, helping them plan specific missions, helping them set out exact flight control patterns, flight altitudes, any of the settings that they need for a specific mission, but we'll get into that. As we dive further, first of all, what are the goals of mission planning? Why are we even talking about this when you could just put the drone in the truck, go out and fly it? Well, we have a couple of philosophies here that I think are really important to balancing all of this. For starters, we believe that a good drone program should do 3 things. It should save time, save money, and it should improve the deliverables. There are lots of ways that you can have a drone program that you use it and you spend way too much time doing it, either too much time in the field or too much time in the office. Those are bad. We care about saving time. Same thing with money. It's really easy to create a program where you buy a $200,000 drone. It requires 3 people to operate it. It takes a full day to fly a 10-acre site, and maybe you're not even getting good accuracy about it. We think it is not, we don't think, we absolutely know it is entirely possible to do all 3 of these things simultaneously. And so that's what we're going to focus on. Whereas good mission planning, when we talk about this, it actually cares about a number of different factors. And when we actually focus on mission planning, we are going to focus on a couple of different things. First and foremost is going to be accuracy and data quality. So obviously, good mission planning means planning for good accuracy to get the accuracy you need. There are lots of ways you can go out and get bad data, but we care about accuracy. Not only that, we care about efficiency in the field. There's no use in spending 4 hours doing something in the field that can be done in 1 hour. There's no use spending multiple days in the field if you can do it in a single day. So we want to make sure that you're actually efficient. That's part of saving time, saving money. But in addition to that, we actually want to make sure that good flight operations drives efficiency in the office. As I will talk about more later on, very often people that have problems processing data, it's taking too much time, they're not getting the accuracy that they want. The root cause of that is actually going to be the mission planning, the data that they collect. So we are going to be adjusting our mission planning for efficiency in the office. We're also going to be adjusting our mission planning and thinking about reliability. Now, when I say reliability, what I mean is that it gets the right data the first time. It's not reliability in that does it actually work? Does the drone work? Although there's a component of that as well, making sure you have all of your equipment. But reliability meaning, hey, we want to make sure that you don't go out, fly, come back, and realize once you're back in the office, oh, shoot, the overlap was wrong because there was a hill in the middle, and that means that that data is bad, or we didn't plan properly for the level of vegetation that was there, or for obstacles, or whatever. It just makes sure that when you send someone out in the field, or when you go out in the field, it works the first time and it collects good data. And of course, another component of this is safety as well, making sure that all of your equipment is in good working order. You have good procedures. You don't accidentally crash into something. But one of the big challenges that we see with mission planning is that really these factors are often at odds with one another. If you want the best accuracy in the world, a lot of people go out and say, hey, I want the best possible accuracy. And what that winds up meaning is they'll do something like flying really, really low altitude with very high overlap, set 10 times more control points and check shots than they need, and their efficiency really suffers. Or maybe they go out and they're like, I got to get this mission done quick. They fly at an ultra high speed, and then they get motion blur, and their reliability goes down, their accuracy goes down. And so much of good mission planning is not trying to maximize any one thing, because you start getting these diminishing marginal returns. If you focus on accuracy at all costs, you are going to have an unsuccessful drone program. And I say that because when you focus on accuracy, that's, to be clear, not saying that accuracy isn't important. Accuracy is super important, but you can't focus on accuracy at all costs, or it becomes such an expensive and cumbersome and painful drone program to run that you wind up not using the drone. You start using your ground equipment as well. So it's all about balancing this, and you're going to hear that from me a lot about how do you balance a lot of these competing factors to make sure that you get an overall good, reliable, repeatable, healthy, accurate, efficient drone program. And to get this done right, we focus on a couple of things that we see are hallmarks of really good flight operations. First of all, they need to be simple. When I say simple, that means they are easy to implement on a wide variety of jobs without in-depth technical knowledge or highly specialized training. And quite frankly, if you're watching this, you should be able to learn enough information about how to implement simple, reliable, and effective drone data and drone mission planning just from something like this. You also want it to be robust. When I say robust, that's that reliable side. You want it to provide good quality data, even if implemented perfectly. Even if you go out, oh, I wanted to use this as a takeoff point, but the site wasn't accessible there. There were fences. I couldn't get the truck there, so whatever. So if site conditions are different than expected, vegetation maybe is different from what you looked on the satellite when you looked at the site, you still want to make sure that your mission planning allows for a certain amount of wiggle room such that even if things aren't perfect, you still get good data. And also, lastly, you want it to be as standardized as humanly possible. When I say standardized, what I mean is you have a single set of mission plan and settings that work for most project sites with very few or no modifications. And that means things like making sure your overlap is the same. Your procedures for how many ground control points that you have are the same. You try and standardize your RTK setup so that you don't have to change 3 different types of RTK setups that are all different and complicated depending on site conditions or site access or things like that. All the while, you want it to be standardized so that you're collecting data that is easy and knowable for a data team to process. And so we're going to go through our recommendations of all of the different good flight operations that can actually do this. And as much as I want these flight operations to be simple, robust, and standardized as much as possible, I wish I could give you a list of, hey, here are the 10 things, set your drone like this, and you'll be able to fly every single site. But that's just not the way things work. There actually are going to be edge cases, and I'll cover a couple of them, but there are a lot of edge cases where things will break outside of the standard, and that's where we cover some of those things. For example, when there are 400-foot tall or taller obstructions, and you have to fly within 400 feet of the ground, you want to try to fly lower for accuracy. How do you manage something like that? Can you fly it in parallel lines below it? What's the safest way? What data are you looking for? And then where the flight regulations come in when you might have to fly 400 feet above ground. As well as things like extreme elevation changes, whether you're working on cliffs or dams. We've actually done projects all the way on the Grand Canyon where you might have 1,000 feet of elevation change over the course of, just a few acres or so. There are ways to handle it, but those are some of the edge cases. There are all sorts of edge cases with airspace restrictions, whether it's flying over airports or doing surveys of airports themselves or prisons or highly trafficked busy areas. Those are all doable. Extreme time urgency can also change things, if you're maybe working in an emergency situation, you've got to go out, you get one shot to collect the right data, and it needs to be fast and it needs to be done there. That changes things. Or one of the things I always like to point out is things like Martian surveying as well. The reason I bring this up is because most people aren't necessarily aware that for about a year and a half, there was actually a photogrammetric surveying multi-rotor drone on the surface of Mars. And the reason I bring that up here is not because any of us are likely to be doing photogrammetric surveys of the Martian surface, but to bring up the difference of what an edge case, what a super extreme edge case looks like. The procedures that they had to survey the Martian surface are going to be a lot different than yours. And arguably they are quote unquote better, but that's because it had a $100 million budget and a team of 20 people for 2 weeks just to plan a single 5-minute flight. And the same is true with all of these edge cases as well. So our goal is to I'm going to focus most of this presentation on that real middle 90% of projects that are not going to be these extreme edge cases. And when there are edge cases, these are some of the things that you just have to be aware of where you then do need to either bring in an expert, like someone at Aerotas, like someone on our flight operations team, or change up some of these procedures. But the overwhelming majority of these projects are not going to be edge cases. Now, as we get into procedures are going to be different based on different hardware that you have as well. So the hardware that you have or the hardware that you intend to have or use for your survey is going to make a big difference for what your procedures are. For starters, I think at this point in the drone surveying industry, the life cycle where this technology has matured, I am of the opinion that RTK should be considered mandatory or near mandatory if you actually view yourself as a surveyor looking to get the right quality data. And I say that the first RTK capable, like quality RTK drone was the DJI Phantom 4 RTK, which was launched in 2018. That was coming up on 6 years ago now. And because of all of that, we're getting to the point where if you're still surveying and mapping with a non-RTK capable drone, it's probably about time you should consider upgrading. And in fact, they're becoming so much more cost-effective and ubiquitous. The majority of my procedures that I'm going to be talking about when we get into actual settings, the majority of the procedures are going to be related to RTK because non-RTK mapping is becoming much and much less common in the professional survey world. Going further, I want to point out that LiDAR does not solve all problems. We love LiDAR technology, to be clear, whether it's DJI LiDAR or Microdrones LiDAR or, a Regal copter. Like there's so many LiDAR systems out there and we love LiDAR technology. It is wonderful. We process tons of LiDAR data, but it is not the magic solution to everything. You do not just fly a site with LiDAR and everything works. It's very expensive to process. It's often less accurate than photogrammetry, depending on a certain handful of different factors on your own mission planning. A lot of people think they buy a LiDAR drone, ergo they fly every site with LiDAR. Not the case. Wonderful tool. We absolutely love LiDAR, but it does not solve all, it is not the solution to all surveying problems. Further, when it comes to hardware, more expensive does not mean it's better. A lot of people say, I have a $250,000 drone, ergo it's good. Especially when it comes to flight operations, what we're talking about today, that is often not the case. The more expensive the drone, usually the more of a pain in the butt it is to operate and actually use repeatably in a cost-effective and reliable manner. Just as an example, the single easiest drone to use of like modern drones is the Mavic 3 Enterprise RTK. The thing is the size, it folds up into the size of a lunchbox, and it is near idiot proof. And it collects good enough data for many applications. Not for everything. It's not the world's greatest drone, but boy, is it easy and safe to operate. And so we really like that. It's also worth noting that anything that isn't DJI does come with trade-offs. DJI is the market leader in drones. We definitely like DJI drones, but I know there's a lot of demand out there for non-DJI drones. You just have to acknowledge that they're the market leader for a reason. Anything that isn't DJI is typically going to be more expensive, more difficult to use, things like that. So there are trade-offs. And without turning this into a hardware presentation, I'll just put this slide up for a second. Our recommended aircraft, these are 3 of our favorite that are out there. No, none of them is perfect. And in fact, that's part of the deal with land surveying now. Everything has trade-offs. Some drones are better. These are our just favorite overall. Mavic 3 Enterprise for most photogrammetric projects. M350 with an L2 LiDAR for most LiDAR projects. And a Wingtra 1 Gen 2 if you have to go outside of the DJI ecosystem, going to something that is Swiss-made, especially good at larger project sites, a little bit hard on smaller or urban sites. But with all of flight operations, when I'm talking about hardware, about edge cases, about all this, I talk about the different competing factors. Really, the goal is to find the right balance in your drone program. And you're going to hear that a lot, that everything comes with trade-offs, and it's finding the right balance. Finding the right balance between accuracy, efficiency, reliability, safety, things like that, as well as tying it all to your equipment, your project site, your people, and your needs. Some projects and some of the people that are watching this may have a decade of experience in photogrammetry and in RTK systems and in troubleshooting technology, and you have a project site that absolutely must have 0.07 of a foot ASPRS certified accuracy. Great. Other times, you're just doing 1 foot topo and you want to give the drone to the 18-year-old kid that just came out of high school and he's looking to fly a site. Those have completely different mission planning profiles, and that's okay because you can have these different things. It's about finding balance with all of this. Again, that's the theme. You don't want to push too far in any one direction. Just a quick story I remember hearing of, this was a couple of years ago. It was a company of some former government contractors that were really, really smart people, and they focused on safety and reliability at all costs. And they were smart people, really, really good. But what they wound up doing is using such expensive over-the-top drones, and they also made sure that they always had at least 2 drones and multiple batteries in the field. And the equipment and setup that they did was so incredibly intense. It was like emergency mission critical life-saving levels of intensity for surveying applications. And what wound up happening is it was such an expensive operation just to deploy all of that the company wound up getting shut down because it wasn't cost effective. It might have been accuracy, but it just wasn't efficient and it wasn't cost effective. So that's just the example of not trying to find balance, not even in a bad way. They were smart guys and they cared a lot about reliability and safety, but they weren't able to balance the program with what the project site, with what the needs were, and with everything else. And always remember that the end goal of this program is a map. The end goal is not to say that you've flown a drone, right? This is different from maybe air transportation where the goal is to get an aircraft from point A to point B. No, the end goal is to be a map. So we're focusing flight operations on all of these things to get a map. And here's your one plug. Of course, Aerotos does do all of this at the end of flight operations. Our deliverables, we do photogrammetry processing, topographic modeling, CAD drafting, planimetric drafting, LiDAR point cloud analysis, classification, and drafting, and all of that. That is what we do. So again, it's why we're doing this. We want to help you get good data out of it so that we can help, we can process more data as well. So with that, let's start getting into a little bit more of the technical stuff now. Let's dive in and actually cover things like airspace restrictions. So first off, with airspace restrictions, some of you have probably seen this slide before about airspace limitations. Operations in Class G are allowed without any permission. This comes from the FAA's Part 107 training materials. It's a little convoluted, so I usually don't like even going over that because it might confuse people that aren't there. So first of all, the most important thing to know is that most airspace is open in the United States. 99% of the US at surface level is Class G uncontrolled airspace, but of course, many projects are within populated or controlled airspace. It is worth noting that you actually can fly in controlled airspace if you get the proper approvals. And in just a second, I'll go through all of the different levels of approvals and the easiest ways to go through and get them when you need to get them. As we're going through this, it is important to note that legal restrictions and aircraft restrictions are different, which means that things like DJI's geofencing on their drone may not align with the FAA maps. And the converse is true as well. The FAA maps don't align with DJI zones. And just because you have approval from DJI because you tap some buttons on the controller, or maybe you have a non-geofenced drone whatsoever, doesn't necessarily mean that you can legally fly there. Plus, the flip side is true. Even if you get legal permission, you might need to get that to override your system's geofencing as well. All of that is totally doable. But as long as you know the right procedures for your drone, it's actually not that big of a deal. It's more of one of those things just to be aware of. Before you actually fly a site, look up to see if it's in controlled airspace. When you are getting airspace authorization, the thing that you really want to go with is LANC. I forget exactly what it stands for, Low Altitude Aircraft Notification. I forget exactly the acronym, but it's called LANC. That's what it is. It's pronounced LANC. It provides for instant authorization at specific altitudes for most airports, and they're actually adding even more. This is going to be the way for if you're flying in or near airports. 99% of the time, you'll want to use LANC, and you can do it through, usually it's done through third-party apps, things like Air Control by Aloft is our favorite. We're not affiliated with them. We just like it. We think it's a very useful and free app to look for where there's the airspace is covered and getting instant authorization from the FAA to be fully compliant with all of the FAA rules. There also are things called manual authorization. So when LANC does not work for whatever reason, whether the airport isn't included in that or anything else, you can file for a manual airspace authorization. It takes considerably more time, so 3 days minimum, but often it can take up to a few weeks. They're approved under many circumstances. You submit them through the FAA's website itself, the FAA Drone Zone. So this one, you need to know a little bit more about it. Again, this actually is a service that we offer. We will file for manual airspace authorizations on behalf of our clients to help you guys get authorization as you need it, just because our flight ops teams knows how to speak FAA. But that's the next step. And then there is another thing called special authorizations, or at least we call it special authorizations. That's not the legal term. This is where you get into more restricted and convoluted airspace. This might be for specific military sites, or even for some of those sites like over federal prisons, which, by the way, we've done all of those before. So we've gone through this and know that this can definitely take weeks and slightly different legal avenues. I will say, from a more practical perspective, anytime the top two don't work, LANC or manual airspace authorizations, most of the time the answer is just survey it on the ground. It would have to be a pretty special site to actually go through, to be worth the time and effort of getting a special authorization. But there are a few sites like that. Like I said, we've done federal prisons. The reason those are special is because the guards don't want people bringing survey poles and survey nails inside of a prison yard. So it actually made sense to wait and fly it from the air. So that's that. And just to kind of wrap up a little bit more on the legal side, flying drones in the real world, people often ask, oh, all of these nuanced questions about the FAA and can you actually fly all of this stuff? The FAA is not looking for bad, or is looking for bad actors, not minor infractions. There is no FAA police. There's no cop hiding behind the corner with a gun to check if your drone is 403 feet above ground versus 400 feet above ground. They're looking for bad actors. Ultimately, what the FAA really cares about is protecting manned aviation. As long as you're not interfering with manned aviation, flying close to air, like right near active runways without checking on it, they don't care. If you're not interfering with firefighting aircraft, they don't care. So people say, oh, can I fly over this highway if the highway isn't closed? Yes, you can. That's what I'm saying. Different lawyers might say different things because it hasn't really been proven, but I can tell you anecdotally, many tens of thousands of people fly over active roadways with drones constantly every single day. And as long as you use your good judgment and you're safe and responsible, then you're going to be okay. So be safe, be responsible, use good judgment, and that'll make sure that you keep your nose clean through all of this. All right. Now, I see we do have a couple of questions in the Q&A about RTK and PPK. So let's actually jump right into RTK and PPK setups. Now, first off, there's so many different options for how RTK and PPK works. In general, our recommendation is that using a local base station, like either a DJI DRTK2 base station that comes with it, or a Trimble Leica TopCon, any of those ones, works best, especially in remote sites. Now, once you actually have your local base station, there are a number of ways you can go about processing the data. First of all, can you use PPK as a substitute for RTK? Yes, absolutely, so long as your other considerations are good. How can you use RTK or PPK in a remote backcountry location? Short answer is use a local base station. Bring a local base station, and then you can actually get a Opus solution on the base station. This can actually be done both with a DJI system or Trimble like TopCon, any third party, even MLID systems as well, some of the cheaper GNSS systems out there. As long as you set them up and keep them recording data for 30 minutes, you can post-process all of that either using publicly available CoreSnet network data, using an Opus solution. But in our recommendation, having a local base station is that is our recommendation for a good and robust RTK setup. And the reason is drones are way more subject to the impact of long baseline distances than ground-based GPS. So what that basically means is that while ground-based GPS might work great either via a complete network solution where you use an N-trip and an internet-connected receiver to whatever the nearest base station is, or post-processing it to the nearest permanent base station, while that is technically possible, we don't like it for two reasons. One, we find it unreliable because it doesn't always work. You're not 100% sure the site might not have cell service. And number two, drones, just because of the reasons of physics, are much more subject, being quickly moving and never static equipment, they are much more subject to errors introduced by long baseline distances. So all of that says that we don't really like network-based solutions or pure PPK that relies on permanent base stations. We much prefer using a local base station. And like I said, if you still are operating a non-RTK drone, your mission parameters will be different than what we're going to go through. As a rule of thumb, you have to submit, or you have to set a lot more ground control points if you're not using RTK. Another question just came in from Josh. Do you recommend flying RTK and collecting PPK data as a backup in case of an RTK failure? Yes, that is absolutely a good and robust recommended procedure. And in fact, typically, believe it or not, that's what a lot of drones do by default. Even one that does this most commonly right now is the DJI M350 with its L2 sensor. Even if you're using the DJI base station, it flies in full RTK, so you have that. And we typically, when we get the data, at least when we're processing our clients' data, we will post-process it as well. We will get an Opus solution or similar. We'll get some sort of static solution on the base and then recorrect all of the RTK data from there. But yes, RTK and PPK simultaneously is a really, really great solution. And does RTK, another question came in, does using an RTK eliminate the need for ground control targets? The answer is no, and I will cover that more in just a couple of slides about once we get past RTK and into any ground control points or anything. And I will say again, if anyone else has any more questions, these are awesome. Keep them coming. The way to get them in, there should be 3 little shapes, triangle, square, circle that says activities. Click on that and then go into Q&A. If you want to ask more questions, please go ahead. I like them. But yeah, just as a reminder, the GNSS-based workflow, they're typically, when we process it, the best workflow is not even to rely purely on a drone and a local base station, but to actually create a network, a processing network of a drone that is live RTK connected to a local base station. And then you take that local base station and you correct that after the fact into a against a permanent base station. That means you're getting RTK from the drone to the local base station, and then you are probably getting an Opus solution or similar on where that local base station was against a CORS network or against some other permanent base station. You can go directly from a drone to a permanent base station, but again, we don't recommend that because of the long baseline distance problem. So as far as what base station do you use, you have some options. You can use ground control points only with no base station. Again, the technology has become so cheap and affordable now. I mean, on the order of a few $1,000s to buy a new drone, like a new Mavic 3 Enterprise that is RTK capable, is a couple $1,000s in the scheme of surveying hardware. It's not cheap. It's not expensive. You can buy the DJI DRTK2. This one it's not going to replace your existing base station, but we have found from an accuracy and ease of use standpoint, it is really, really useful. Many of our clients and our actual recommended workflow, typically surveyors go out to a site, they'll have their high-end surveying gear, Trimble, Leica, etc. They'll actually bring a DJI base station as well because you just set that thing up and it just works. Very, very, very reliable. Question came in, where is the antenna reference point of the DRTK2 base station? That is a great question, and I actually don't know that. I would have to look up the specifications. That said, without getting into too much detail of how you PPK process everything, you don't necessarily need to know that depending on the workflow. The reason I say that is because the DJI DRTK2 should not be used as a substitute for a proper GPS system for finding points on the ground. When you are getting the solution out of it, you are just correcting relative to exactly where the head is, the antenna reference point is. You don't need to do the offsets to find the ground because you really shouldn't be using a DRTK2 for ground surveying. You should be using it for getting the as close to the absolute position of the system as possible. And you can always correct against GCPs. I won't go into too much more detail because this is about flight operations, not data processing, and that's a whole nother can of worms. Differences between mechanical shutter versus rolling shutter is another great question about hardware. If you are buying a new drone, it needs to be mechanical shutter. There's just no excuse anymore to buy a linear rolling shutter drone. Yes, there is software that can correct with it, and it corrects for it okay, but not perfectly. It introduces more accuracy. It introduces more error into the overall system. It is a lot less scalable, particularly for larger job sites, anything above 10, 20, 30 acres. Linear rolling shutter introduces more problems in processing. So our opinion, there's really no excuse to buy a new rolling shutter drone anymore, given that there are plenty of mechanical shutter things there. What do you consider a long RTK baseline? Great question there as well. For drones, a long RTK baseline is 10 miles or longer. Anything over 10 miles and you start to see material degradation in the overall quality of the image geolocation. Now, I say 10 miles too, that's a really moving target, unfortunately. Part of the reason I say 10 miles is because, well, honestly, sometimes you can make it longer, 15 miles, but you're rolling the dice based on whether the tropospheric weather and conditions are similar at your site to what they are over the base station, which you don't know what that is. I don't know what that is. You can't really forecast the weather as to how it affects regional baseline distances. Sometimes it works at 15 miles. Sometimes we've seen material degradation at 7 or 8 miles, but really 10 miles or longer and you start seeing seriously material issues. Is there any advantage to manually setting the DRTK2 coordinates to a known point versus just setting it up? Setting a DRTK2 system or whatever your base station is over a known point is preferable from a data processing standpoint, but it's a real pain in the butt from a field operations standpoint because you have to have a already known measured point. And usually when you're going out for a drone flight, you don't have that. You might be visiting the site for the first time. You're setting up your base station over what you will eventually find to be a known point. And so you can't program it in beforehand. So while that is advantageous if you have it to set it up over a known point, you usually don't, and that's okay. And that's where we get back to this concept of making a reliable, robust, and simple workflow. Our recommendation is just set it up on its own derived coordinates, set up your base station over something that's completely arbitrary, and handle it all later in post. It's a very robust workflow, and it makes it simpler and more reliable. Versus if you set it up over a known point, you need to have that known point in advance. You need to be very careful to do all the conversions right to get it from whatever your local NAT83 coordinate is to the WGS84 that it inputs. Make sure that all of your ellipsoids and datums are correct. And if you then fat finger a single number, it might ruin your entire flight. So we actually, just from an operational reliability, say no need to set it up over a known point, process it all later. If using a permanent base station, how close do you have to be in miles? Yeah, like I said, about 5 to 10. All right, these are some great questions, but we're already running out. Gosh, because it's already been 35 minutes. I'm going to keep going. There will be a contacts link for plenty more emails and questions after the fact, but we can keep just going through this. All right, so I've already answered a lot of these. Here are your different GNS post-processing options with a handful of the different trade-offs that are out there. And for the record, we will make this recording and all of the slides and handouts fully available at the end. So we think RTK with a local base is there. I will answer one more question from Bob, who asked a great one. We always post-process PPK to our local base over a known point with great success. What do you gain by adding RTK capability? And that's a really, really good question. What you gain is troubleshooting in the field. What we have seen on a handful of sites is people that use that workflow might at some point have their local Trimble base station run out of battery or have a setting or the memory card gets full in the middle of a flight and they didn't realize it until they were back in the office. What RTK adds, what real-time adds from an operational reliability standpoint is that when you're actually flying your drone, if it is a DJI drone, it has a green bar that says RTK good. And if that bar turns red, you can hit the home button, fix it in the field, and then go back out and fly and make sure that your entire GNSS system is reliable end-to-end before you get into the office. Now, is that any more accurate than PPK only? No, there's no benefit there. But from an operational standpoint, the reason we like or prefer at least real time is that if there's just a simple issue, you can fix it right away without dealing with it. Maybe and we've seen all sorts of different edge cases here, whether you set your GPS system in a place that might have some sort of building shadow or multi-pathing or whatever it is. It allows for real-time correction of errors in the field. So that's enough for RTK setup for right now. Next up, I want to get into ground control point and checkpoint planning. One of the questions that already came up was, do I need ground control point at all? And the answer is, good RTK or PPK is technologically capable of producing survey-grade accuracy without ground control. However, in the real world, we believe no ground control is not good enough for land surveying and mapping applications. And that is actually for a handful of reasons. Ground control is required to do things like properly calibrate the camera. If you've done as many very, very detailed tests as we have done, what you would find is that even if the drone and the RTK is perfect, there is a camera lens between the drone and the ground. And the difference between a hot day and a cold day on the geometry of that camera lens can actually move your entire surface up or down by 1 or 2/10 of a foot, which is outside of the tolerance that we typically look for. We look for a 1/10 of a foot tolerance. So even with perfect RTK, unless you have a table of your camera's calibration setting based on temperature, including RTK or including ground control and check shots is very much recommended. Also, for localizing your project, some people work in perfect pure NAT83. More likely than not, a lot of you are going to localize over a known point so that it matches with all previous maps, especially if you're in California here where things move all the time just from seismic changes. You need to be able to localize the project or move it to a purely local coordinate system, which is something that we see regularly. It also, you have the ability to detect human errors as well. There are a lot of those. We see them all the time. So having the ability to detect human errors, whether you set the datum wrong, whether you didn't post-process your own control, whether you had 2 different crews shooting ground data, we think ground control is pretty much required, especially because human error does remain common, especially in more complex RTK and PPK workflows. So while you technologically can get away without ground control, we think that is not the professionally responsible way to do it, especially, again, with a focus on reliability to make sure that it is right and that it is verifiably right. As far as how many ground control points to set, now that RTK is more common, systems are a lot more robust to having fewer control points. Before RTK, you needed a minimum of 5, and maybe you needed 10 or 20. With RTK, our recommendation is a minimum of 3 per project, as well distributed as practical is probably a better word than possible, and ideally 3 for every time you wind up picking up and moving the GPS base station. So that is ideal. You can get away with less, particularly if you are confident in your workflow, if you are confident in your camera, if you've processed numerous similar sites, you're aware of a lot of the implications that can come with things like weather and elevation changes and all of that. But as a rule of thumb, 3 per project minimum and another 3 anytime you pick up and move your base station. That'll keep you in the clear with enough redundancy. Anything beyond that, you can use to actually check the data. As far as where to set GCPs, the actual site location, as long as you have good RTK, you no longer need to set them at the corners and outside edges of the project. I'm not sure how well you can see here. It's a little bit dark, but this is a project site that we did as a test where we actually set test sites, check shots all throughout the project site. But it's a very, very inaccessible site with really, really dense poison oak and blackberry brambles and rocks and hills and trees. And so we only used 3 control up in the corner. And sure enough, because the RTK and PPK solution was good with a local base station, the system was actually able to get 1/10 of a foot accuracy, even with 3, honestly, pretty poorly distributed control points. So good accuracy is still possible, but it's going to make it, when you have poor ground control point distribution, it's going to rely way more heavily on the RTK and PPK solution. Now, it's worth noting, can you have ground control distribution like this without RTK? Absolutely not. Your data would be garbage. Anything outside of these points would be completely just terrible and effectively useless from a surveying perspective, at least. So you need RTK if you're going to have anything other than perfect GCP distribution, which is part of why we love RTK and think it's near mandatory. Another question for a corridor GCP placement, having it zigzag or staggered is going to be the best. Our recommendation, even with RTK, is going to be a maximum of 1,500 feet. With a zigzag pattern recommended, and throw a pair at the end of each of the roadway just to improve accuracy. Let's see, got a couple of questions that I will go in here. With an M350 and L2, do you recommend non-repetitive scanning with penta return? even on sites with little vegetation? The answer to that is, on a site with little vegetation, I would recommend using photogrammetry instead of the LiDAR sensor at all. If you are doing a site on a hardscape, photogrammetry remains cheaper, more accurate, and can actually give a better visual picture. When you do have sites with vegetation, though, yes, we always recommend penta-return or triple if you're on the L1. We have not found a huge difference between repetitive and non-repetitive scanning as far as which one's there. So I don't have a very strong recommendation. I know they've made a lot of marketing fluff about the difference there. We haven't seen enormous differences. There might be some edge cases where those different scanning settings make sense. And then ASPRS standards call for 20+ check shots. So I have a whole different presentation on accuracy, which if you want to stick on for the next couple of weeks, will probably be the next webinar that we do. Long story short, the 20+ check shots is for the highest tier of ASPRS accuracy certification, which is impractical for the overwhelming majority. So there will be a lot more to come on accuracy. Definitely shoot us an email if you want to be involved in that or hear more. But we think 20 check shots for full certification is overkill for the overwhelming majority of projects. Sometimes that is necessary. As far as some more just advice, basic information on marking ground control, there are a handful of not great ways to do it, whether you have targets without a clear center, edge of concrete or edge of corner that might be difficult to discern which corner it is. Honestly, even chevrons we don't love because different surveyors mark chevrons differently. The forward tip, the backward corner, back corner, or in the middle. Or then obviously I love putting this slide on whenever I speak because this was an actual client project submitted to us, and I just thought it was fantastic that someone used a shooting range target for a GCP. But really our favorite, checkerboard patterns where the center is visible anywhere. These are the ones that we make. You do not have to in any way use our targets, either for good data or for processing with us. We just love them because bright colors are easy to see and checkerboard pattern makes it easiest to mark in the center. All right, so enough about GCPs now. Let's get into some of the last parts for flight planning. And as a reminder, always plan with data processing in mind. I mentioned this before. The purpose of a flight is not the flight. The purpose of the flight is to create a map. And that means when you're planning, you want to make it so that it's easier to process accurate data. There is such a thing as too much data. Bad flight planning does create data processing problems, and you should collect the data you need, but not more than you need. Collecting more data than you need can definitely wind up causing problems. And one example is LiDAR versus photogrammetry. There was that great question, do you actually need, or what settings do you recommend for LiDAR on hardscape? And our answer is, if you have the L2, the photogrammetry camera on the L2 is going to be good enough for most hardscape things. LiDAR is what you need in vegetation. If you're doing a topo map in a vegetated area, then yes, you need LiDAR. But as of the current state of the industry, photogrammetry is faster, easier, more accurate on hardscape, and cheaper. So our preferred data processing workflow, when we have a site with vegetation that was flown with a DJI L2 or any of the other leading sensors that can do LiDAR and photogrammetry simultaneously, which we love, the L2 can do it, and those are what the good sensors can, we actually blend the data. We use photogrammetry for any of the 2D features. For a lot of features that might be hard for LiDAR to pick up, things like manhole covers that are very easy in photogrammetry. And for most things on hardscape, we use photogrammetry, and then anything in vegetation, we use LiDAR. Great question on better curve precision. I'm going to have to say, reach out to us after the fact, because that's a little bit more on the data processing side. We'd be more than happy to help you out there, but I don't want to keep people longer than I need to. Another question, what autopilot should I use? There are a million autopilots out there, and quite frankly, they are all comparable to one another. For now, newer drones, use the built-in autopilot. It is plenty good enough. If you buy a new DJI drone, use the DJI software that comes with it, whatever the most recent one is. If you use a Wingtra, use the Wingtra planning app, because, well, that's the only one you're allowed to have. So there are different options out there. When you are planning a flight, what is the optimal flight pattern is another question. Do you do a lawnmower style, also known as single grid, also known as boustrophedonic, if you want to be fancy about it. That is a single grid. This is the most common and honestly most recommended flight pattern. Double grid, or what is also known as crosshatch, we think you should use this very sparingly. In general, in most cases, not every case, in most cases, it will double the amount of data that you collect. It will triple the processing time because you have double the amount of data, and it will lead to absolutely 0% improvement in accuracy. In the vast majority of cases, do not use a double grid or crosshatch pattern. The exceptions where you might want to use it are in remote, very heavily vegetated areas where you need that extra data to possibly have some slight different angles. And this is true for actually LiDAR and photogrammetry to try and penetrate it. But we're talking like, you know, very, very, very dense vegetation is the only circumstance where we would recommend a double grid pattern. Otherwise, it makes everything worse, like everything worse. It's more time in the field, collects more data than you need, harder to process. We really don't like double grid. And I think a lot of the apps out there push people to double grid pattern, which is a disservice. And then linear mission, that's where it flies along for linear corridor mapping. Those are great. We do love linear missions or parallel flight patterns for linear missions. Next up is going to be flight altitude. Flight altitude is another one that it's easy to make some mistakes on, partly because this is the one that will vary depending on, it'll vary the most depending on the site and depending on the data you need. We always say, start with your desired results. If you need better than 1/10 of a foot, then you should be flying at about 150, maybe 200 feet above ground. The downsides to flying so low are you can't cover as much area per flight, and it takes a huge number of photos. This is the number of photos per 100 acres. Whereas if you are doing 1 foot contours, if you need topo over a 200-acre site, you absolutely should be flying at 400 feet because 2/10 of a foot is more than enough for that project. And flying it at 1/10 of a foot will make it, it'll just be miserable to fly and miserable to process. So usually for most of our project sites, most of the projects that we see are somewhere in the middle of that. They are going to be about 200 to 250 feet is our usual kind of Goldilocks zone that you fly at that altitude, and you can typically get 1/10 of a foot accuracy at 200 to 200 feet and get good data there. Now, for larger sites, we definitely recommend terrain awareness. Terrain awareness, again, most modern autopilots have this, but not all of them. That's where it approximately tracks the terrain to keep a roughly even flight above ground, a roughly even altitude above ground level. This helps hugely in larger sites with significant relief. When I say significant relief, I say pretty much anything, if the ground itself has more than about 50 feet worth of elevation change, then you should consider using terrain awareness. If it has more than 100 feet, you absolutely should be using terrain awareness. It's a little bit more difficult to use, which is why we don't recommend it on everything. You have to import the right world models. They're making it easier with more modern autopilots, but it's a little bit of a pain, so don't use it if you're doing a flat site, or if you're doing, you know, a 2-acre lot. You have absolutely no need to use it, but it definitely can help when you have it. Another question is nadir versus oblique. For the overwhelming majority of maps, nadir is the answer of what you need. Obliques can offer better identification of vertical features. So if you were doing facade modeling of the cliff in an open pit mine because you needed to inspect it for cracks, okay, use obliques there. But at the cost of more processing time, lower resolution, and we've done a lot of testing. Resulting accuracy is very, again, one of those edge case things. It is rarely improved by adding obliques, so our recommendation is nadir only. Next, and I saw there was a question about this, is overlap as well. So for overlap, it's different with photogrammetry and LiDAR, and even traditional photogrammetry with a metrically calibrated camera, like a perfectly known pre-calibrated camera, can get away with lower overlap versus modern digital photogrammetry. Our recommendation and the consensus of the industry is about 75-75. That's 75 front, 75 side for photogrammetry. If you want to quibble and say, I do 70-80 or 80-70, those are all fine. Those are all well within the normal zone. Anything below 70% is going to be problematically low. Anything above 80% is kind of going to be too high. You're collecting more data, too much flight time, again, causing data processing problems as well. So 75 is a good middle ground. And with LiDAR, while the jury's still out a little bit on that one, 60 to 65% is our recommendation. That's higher than a lot of the actual hardware manufacturers recommend. We find it adds a lot more data redundancy. Going back to that, making a robust field workflow, it makes sure that if part of the data is shadowed by a tree, you're going to catch it from the other angle. So we recommend slightly higher LiDAR overlap than industry average right now. Recommendation for flight speed, short answer there, trust your drone's flight computer. Any good drone flight computer, depending on the drone, depending on the lighting conditions, depending on the camera, will adjust its flight, and depending on the altitude, will adjust its flight speed accordingly. You can go very fast on the newer drones at higher altitudes. 30+ miles an hour is perfectly acceptable. So here's our brief summary of recommendations. When flying, photogrammetry for hardscape, LiDAR for vegetation, use your built-in autopilot, fly single grid lawnmower flight, 200 feet AGL for most projects is what you need, but anywhere from 150 to 400 is appropriate depending on project needs, and nadir only imagery with 75 overlap. So now with the last couple of minutes, we're just going to cover flight execution, which is actually the simplest part. First thing, use a simple checklist. Simple checklists avoid you from making dumb mistakes. Dumb mistakes like forgetting to put the SD card in the case before you go out and fly. Dumb mistakes like forgetting to take the 3 seconds to pull out your phone and see if the weather at the job site is different from the weather where you are. It makes results reliable, repeatable, and it makes it so that even if you haven't flown in 3 months, or when you're handing the drone to a new employee or training them, you get repeatable results no matter who flies the job site, and it just makes it more idiot-proof when you're flying it. Use checklists. Also, a couple of weather considerations that are in there. A lot of times people will ask me, what is the perfect weather for a drone flight? And my answer is, don't care about perfect. Perfect doesn't matter because you can spend a year waiting for perfect weather. Perfect weather is wind speeds under 5 miles an hour at high noon, where the sun is high in the sky, a temperature of 50 to 80 degrees with perfect overcast lighting so that there aren't any shadows, but everything is very bright with no precipitation. And I don't know where you live in the country if you see that every single week, but I don't think that's going to happen. Don't let perfect be the enemy of good when it comes to weather. When you have the time to go to a site, fly it. Any wind under 30 miles an hour is handled by most drones. Check your specific drone if you have different limitations there. Time of day, sure, high noon is great, but anytime the sun is up is good enough. And in fact, you can even fly LiDAR at night, but that's a whole different question. Temperature, 10 to 110, any cloud cover, whatever you got, just go out and fly it. Don't worry about perfect, worry about good enough. And then there are some simple quality of life improvements as well. Things like field recharging. If you are doing large sites, it's a new thing. Electric pickup trucks are actually fantastic for recharging drones on the go. Other people have trucks with very powerful inverters or things like that. And just little stuff. Remember to throw an easy up tent and a chair to sit in if you're going to be doing a long day of flying, because quite frankly, a good flight is boring. That's why you need to sit on these things. And our favorite part with all of this, if you actually follow this stuff, our goal is really to take the excitement out of drones. A good flight is boring, especially if you follow your checklists, use autopilot only. You should never be taking manual control. And then if something goes wrong, if you are worried of anything, hit the home button. Manual control just really does not need to be used anymore for surveying. That reduces reliability, reduces all of that stuff. Once you're done with your flight, we think you probably should verify data if you in the field if you can. Field revisits can be pretty costly, and a laptop with an SD slot can definitely recommend things. This is more important for remote flights. I've just got a question. Yes, we will be sending out a recording and some information to this afterwards as well. So since it is 11 o'clock, I'm just going to wrap up at the end here by saying processing data with Aerotas. If you've listened to me this far, thank you so much. Ultimately, this is what you do to get good data from the field. But to get the best data out of your drone at the end, you really actually want to process data with us. That is what we do. Aerotoss line work is our core product. We process photogrammetry, LiDAR data, and actually turn it into maps. The way that we work is you fly the drone. We work with land surveyors and civil engineers across the country. You fly the drone, and we process the data. We do the photogrammetry, the LiDAR. We have a whole team of photogrammetrists and CAD technicians and LiDAR technicians and drafters to do all of this at a scale and a efficiency and accuracy that is industry leading, and that's why we do what we do. So if you are interested in processing data with us, if you go out there and follow these procedures and want to see what you can actually get from the processing side, then you should reach out to us. Our team is experienced. We are very accurate. We focus on 1/10 of a foot on every project or better. We try and we make sure that our processing is reliable to get you the right data the first time so that you know how accurate it is. You can do large projects or more projects when you need to. So with that, if you are interested in learning more, please reach out. You can go to aerotoss.com/contact. If you wanted to email me directly, my personal email, if you want, is Logan, Logan, @aerotoss.com. Might just put a link to the contact form in the chat as well. So I know I didn't get to all of the questions here. Honestly, thank you all so much for being a very engaged audience and having these questions. So please feel free to submit data to us. Thank you. I'm even getting some good notes in the Q&A here of clients that are actually working with us and love the work that we do. That is why we do what we do. If you're interested in seeing and getting the most out of your drone that you possibly can, please, please, please reach out. We'd love to show you what we can do. We would love to process some data on your behalf. And with that, stay tuned. We will send out more information and continue doing more webinars. So I hope that was really useful. I hope that that actually provides some valuable information to people. And yeah, Mike, anything else you want to add before we sign on?
Just on the programming note, there will be a recording circulated. I'll send everybody who is on the call here the follow-up email, and we will, I know some people ask for a downloadable sort of one-pager. I will absolutely attach that, that checklist that Logan referenced, recording. We'll also send out a survey if people had questions that we didn't get to on the call. Feel free to put those in the survey. Questions that you still have, as long as what other topics you would like us to speak on, because we'll be doing more of these. So that should be going out later today or maybe tomorrow. Just look for that in your inboxes. And thanks again, everybody, for tuning in. This was great.